Section 9.3 is about paired data, as opposed to when you have independent data like in Section 9.2. And actually, Section 9.2, I would argue, is harder than Section 9.3 because Section 9.3 looks very similar to stuff we've already done. When you have paired data, basically what you do is you treat the difference like it's the variable. But then that's more like having one sample and having two samples. And really what it comes down to is that if you have paired data, the way that you would get a confidence interval and the way that you would compute a p-value for a hypothesis test are identical to what you would do with a single mean. So like what we had in chapter 8, or I guess chapter 7 for the confidence interval, chapter 8 for the hypothesis test. So because this calls back to other things that we've already done, I think 9.3 is actually easier. The toughest thing in a way might be just figuring out when you have paired data and when you don't. Because then if you know you have paired data, effectively what you end up with is a little bit simplified, which is good, right? Which is nice. So, all right, there it is right there with paired data. The difference is treated as the variable. That's the biggest statement in this section. If you remember that, that's probably going to be enough as long as you're comfortable with how to do a hypothesis test and a confidence interval for a single mean. Because then you go, oh, I just do that thing that I already know how to do. And that is pretty much the way that it works, just like it says in that second bullet point. The third thing, there is some new notation. Basically those D's and the subscripts, like how there's an N sub D and then an S sub D, the D just stands for difference. So like number of differences and standard deviation of differences. The D bar, let's see, that's weird. That's a typo that I've gotten there. I guess that looks sort of redundant. That one shouldn't be a D bar. That one right there should be an X bar sub D. That's really what I was aiming for there. So X bar sub D, I kind of like that notation better because then it's just everything has a subscript of D for difference. So that feels more consistent or more uniform or something. But our book uses the D bar and that's fine, right? I mean, D bar looks like an X bar. Like I can understand that preference too, of using a D bar instead. So we'll stick with what our book's got. All right, then if the sample size, which now if we're treating the difference like it's the variable, then the number of differences is our sample size. So if N sub D is at least 30, you can apply the central limit theorem. If it's too small, then either you have to take a look at a histogram if it's a little bit too small to see if it looks like the sample values are normally distributed. And then from there, we might be able to assume normality. Or you would just have to blindly assume the population's normal if N sub D is really little, if it's like 6 or 8 or something. And then the standard error looks familiar, right? Looks like what you'd have for a single mean. And so does the degrees of freedom, right? It's just now there are subscripts of D where before it was just S's and M's, right? The confidence interval, if you look at the formula, looks an awful lot like the formula for the confidence interval for a single mean, right? And a lot of that's just because the standard error looks so similar. But you're still going to use a t-distribution, right? Anything that has to do with a mean, whether it's a single mean or a difference, either kind of difference, like independent, like section 9.2, or paired like this section, anything with a mean, t-distribution. So yeah, that confidence interval looks pretty similar to what we had before. And then the hypotheses, you can have other stuff, but for what we're going to do, the null hypothesis is just going to be that there's no difference. So then mu sub D, the population mean difference, is 0, right? Equivalent, that's the same thing as saying there's no difference in the population. And like I said, you can have other stuff for the null hypothesis, but it would be really unorthodox to do so. If this test is being used realistically, like in a practical sense, it's going to be used for this. And I guess then the next thing is like differences of what? Something that could be paired up easily. The most straightforward idea would be before and after measurements on the same individuals. And that's most of the time what you get. But it could be things where you have 2 measurements on every individual, like reaction time between the dominant hand and the other hand, right? Things like that. So you can do that kind of stuff, where you do have pairs of measurements for every individual, but they don't have to be in sequence. Or I guess you could have actual pairs of individuals, where you'd have to have a way of pairing everybody up, or you end up with individuals that are as similar as possible inside the pairs. That is another way of doing it, although admittedly you don't see it as much. And then the test statistic looks like what you'd have for a single mean, except there's no mu0 on the end. And that's because the thing that I have is delta 0. So like delta for change, that's always going to be 0 for what we're doing, because our null is always going to be mu sub d equals 0. So then that minus 0 just isn't there. And you just have a d bar. All right, so, okay, a lot of stuff looks like it would for a single mean. That's good, right? Some familiarity. But then with StatCrunch, if you have the summary values, it's exactly what you do with a single mean. So this right here, this is exactly the same as what you do for a single mean. The raw data is a little bit different. You kind of do what you would, like you go to the same menu. So you go to stats and then t-stats, but then you would pick paired, and then basically you just specify the columns where your data are. So what you'll end up with is like you'll have two columns where maybe the before measurements are in the first column and the after measurements are in the second column. So you just pick your two columns and do it like that. It's not too bad. We'll go through an example of it in a little bit. But first, we'll do it with a summary. All right, so this first example, it says 10 college freshmen take a math aptitude test before and after a training course. See, this is what I'm talking about. This is usually what you get, before and after. So some kind of before and after. That's the most common scenario where you'd have paired data. And then the mean of the before scores is 71.9, mean of the after score is 78.6. And then we have standard deviation of before scores, after scores, and differences. Okay, note that there are only 10 differences. That's too small to apply the central limit theorem, right? 10's less than 30. So you'd have to assume the population is normally distributed. And here what the population is the distribution of differences in the population. We got to assume that that's normal. All right, so we have to make that assumption because the sample size is small, but then how do we actually get the confidence interval? I guess we need to specify an order of subtraction here. So I'm just going to say if D for difference is after minus before. Usually that's the way you do it, and you can go the other way if you want to, but if we do it the usual way of after minus before, we're going to get a positive number, because then really D bar is the same thing as the difference of the individual sample means. That doesn't work for the standard deviations, but it does work here. So what we could do here is we could say that then this would be 78.6 minus 71.9. So it looks like that's 6.7. Then the other thing that we need is S sub D, right? Because this is paired data. So if we look up there in the wording, there's stuff that we don't need, right? We need this right here, the standard deviation of the differences. So that's S sub D, the 5.6578. Those other numbers, like the standard deviation of the before scores and the after scores, we don't need them. Not for what we're doing right now. Because those, like, if you were going to, I guess if you had independent samples, like if you were going to do that, then you would need those, but these aren't independent samples. So we just don't need those numbers at all. The only standard deviation that we're going to need is the 5.6578, the standard deviation of the differences. And then I guess we need N sub D, but we already know that that's 10. So N sub D equals 10. And then I guess we're going to StatCrunch, so I'll put the StatCrunch stuff over toward the right, change colors. All right, so we want a 90% confidence interval. So remember that 90%, right? That means we're going to have to change the confidence level because the default is 95. But let's see. If we go here, then if we go to stat, then tstats, and then we're going to do one sample with summary, right? Because if we're treating the difference like it's the variable, then it's like there's one variable, so it's like there's just a single sample, right? So let's see, our sample mean, that's d bar, that's 6.7. Sample standard deviation, 5.6578. Sample size was 10. And we want a 90% confidence interval, so I got to change that confidence level to 0.9 and compute. And there we go, 3.420 to 9.980, it looks like, to 3 places. All right, so let's go back there. All right, so our 90% confidence interval, it's 3.420 to 9.980. All right. Now that we've got our confidence interval, then is it reasonable to conclude the mean test score increased? Well, we had set up the differences after minus before, and we're getting all positive values, right? So if we're getting positive values here, then that's evidence of an increase, right? Then it looks like the after scores on average are higher than the before scores. And that's why when we subtract in that order, we'd get a positive difference. So here we could say, yes, since the entire confidence interval is positive, but here increased and positive are going together, but that's because of the order of subtraction that we had picked. So with the order of subtraction reversed, so that would be like if we said that D equals before minus after, which you can do, right? There's nothing wrong with that, right? It's another option. Then the confidence interval would have been negative 9.980 to negative 3.420. And the conclusion would be yes, since the entire confidence interval is negative. So the order of subtraction that you use, that can have an effect on kind of the way that you would look at things. So here, the way that we did it, the one that's in maroon up there, the fact that that's positive, that we look at it and go, oh, it's positive, therefore that's an increase, that's because of the order of subtraction that we picked, because it's after minus before. If we picked it the other way around, then a negative would actually show an increase, which feels kind of awkward, but that's why people usually don't pick that order of subtraction. That's why it's usually after minus before. So I did want to point that out, though, that what you would be looking at, like in terms of what kind of numbers are going to match up, like with your endpoints to show an increase, that is dictated by your order of subtraction. So that was a lot of writing to get that thing in parentheses in there, but I figured that was worth it because, right, you do have options here. You could do it in the other order, and then you just have to look at it the other way. Okay, next example. All right. This is one where I'm not sure we even need a hypothesis test to figure out what's supposed to happen. After all, we're talking about putting a stimulant into the body to see if that increases the mean heart rate. you would kind of expect it to, right? I mean, you certainly wouldn't expect a decrease. And I guess that's sort of the justification for having a one-sided alternative here, right? Because there's no way you'd expect a decrease here. So increase is the key as far as setting up the hypotheses are concerned, because then if we're thinking of the difference, like it says here, as after minus before, then an increase would be a positive value. So then for the alternative, we're looking for evidence of the mean difference being positive, right? Population mean difference mu sub d being greater than 0. And then the null would just be no difference. So mu sub d equals 0. The test statistic, as it turns out, is absolutely enormous. This is one where I think you can make the decision without even getting the p-value, because when you think about what that means, that test statistic of 8.463, that means that our sample mean difference is 8.463 standard errors above 0. That's pretty far. Usually you end up rejecting the null when it's more than 2 away from 0. 8.5 roughly? Yeah, we're going to reject the null. So let's see. I'll try to write out the thing that I said. That d equals 3.75 is 8.463 standard errors above 0, which is a lot. Like, that's really a lot. So then what we would think would happen is that the null should be rejected, which is absolutely correct. And if we were going to get the p-value, we can do it. So then this is supposed to be a t-distribution with 47 degrees of freedom, because the number of differences is 48. If you go up toward the top, it's sort of cut off right now, but we got 48 regular tobacco users, or regular chewing tobacco users. So we've got before and after measurements on 48 people. That means we have 48 pairs of before and after measurements. So n sub d is 48. So 48 minus 1 is 47. That's why it's 47 degrees of freedom. And the thing that we'd be looking for, so that's a t-distribution. It's centered at 0. 8.463 is actually farther out into the tail than that by quite a bit. But I wanted to make this so I could actually have a tail to color in. So let's see what we get. If we go to StatCrunch, get that out of there. And then let's see, I want calculators, t, 47 degrees of freedom, and then greater than or equal to 8.463. Tiny. 2.617 times 10 to the negative 11th. All right. Little tiny number. All right. So then the p-value is 2.617 times 10 to the negative 11th. So if you were going to write that out in decimal form without scientific notation, it's a decimal point, then 10 zeros, then a 2617. So that's a little number. All right. Well then, since the p-value is, certainly that's less than 0.05, right? Because this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 6, 1, 7. So yeah, that's definitely less than 0.05. So less than 0.05, that's when we are going to reject. So we should reject the null, and there is sufficient evidence to conclude what's in the alternative. So I thought that would change it up nicely to have the conclusion be one where we just filled in the blanks instead of writing out the whole thing, because those are kind of long. But yeah, little tiny p-value. But that's what we expect when we get a crazy looking test statistic like that, right? So, all right. When you're that far out, there's just not a lot of tail left beyond that value, right? So you get a little tiny p-value. All right. This is a big deal, this page. And this, like I said at the beginning, this might actually be the biggest thing. just figuring out if you have paired data or independent data. And that's what these examples are. All right, so we've got this one about the alpine botanist. We've got slalom races, like with new skis, like all the skiers use the old skis and then the new skis. And then we got this third one with a group of kids who get fluoride and a group that don't get fluoride. Okay. First things first, if you're going to be able to pair up the data, however you're going to do it, whether it's like before and after measurements on the same set of individuals, whether it's two separate groups that are paired up somehow, you'd have to have the same sample sizes. Otherwise, you couldn't pair everything up, right? Because then if they were different and you put them in two lists, one list is longer than the other, right? So you couldn't pair it all up. And that relates to A, because 30 flowers, 40 flowers, can't pair them up. And if you look through that paragraph, those are just two totally separate groups. There is no pairing at all, even without looking at the sample sizes. So even if we weren't given that. So we have 30 of the known species and 40 of the new species, right? There's nothing in there about pairing. It's just two totally distinct groups. Here's group one, here's group two. And since they're different sizes, that's a gigantic red flag that would automatically mean you'd have to have independent samples, right? So different sample sizes, you can't pair everything up. So that's what I would be looking at right away. And I would be thinking, well, if you have different sample sizes, there's no way you got paired data. So different sample sizes, we'll just say must be independent. All right, B, with the skiing, so we have 20 students running the course twice, once with old edges, once with new edges. So if everybody does it twice, you got two measurements for each individual. That's a pretty natural way of pairing things up, right? Every person's got the measurement with the old edges and the measurement with the new edges. So when you have two measurements for each individual, like we do here, that's when you got paired data, right? That's a scenario where you've got paired data. So two measurements for each individual, that's when you have paired data. And then the third one, this would be the kind of thing you have to watch out for, because you can't just look at the sample sizes. If the sample sizes are different, then yeah, I guess then you can just look at the sample sizes. But when they're the same, it's still possible that you could have independent samples. And that's actually what this is. Because we just have two groups that are totally separate that happen to be the same size. Right? They just happen to be 32 in one, 32 in the other. There's no natural way of pairing. It's not like we have 32 groups of siblings or 32 pairs of siblings where one sibling gets the fluoride and the other one doesn't, right? We don't have anything like that. So there's no natural way of pairing, so these are going to be independent. So I'll just say no natural way to pair up observations. And so that means that these are independent samples. And they just happen to be the same size. So I'll put that in here too. Samples just happen to be the same size. Okay. Then the next thing is, well, what if you got this wrong? Right? What if you had paired data, but you accidentally consider it to be independent, or vice versa? What happens? Well, this is what happens. So, all right, here, this looks like it's supposed to be paired data, right? if you think of each row as being a different individual. So like where it says scenario A and scenario B, down where it's written in bold. If you think of scenario B where it's 12 people where each person used their right hand and their left hand, then that looks like paired data. But it doesn't really have any context. So then you say, well, what if it was the other way around, right? What if that was actually just 24 individuals that were randomly assigned to use the left hand group or use the right hand group? Possible. So, okay. Well, what would be the differences? All right, well, check this out. So I have all the summary data in here, but the important things, I guess they would be the p-values and also the test statistics. I guess I should have boxed those in too, because you can see what's coming if you just look at the test statistics, right? One of those is pretty close to 0. The other one is absolutely not. And so one of those will give you a very tiny p-value and the other one won't. So when you have independent, so like this is the independent side, right? So I guess let me write this in a different color there. So this is independent. You can tell looking at the hypotheses, right away, because you've got the separate mu sub R and mu sub L. And this one is paired because you got the mu sub D, right? So when you treat that as independent data, then the standard error is really big. Because that's the only thing that's different, right? Like if you look at the two test statistics, the numerators are the same. But the denominators are very different. And the denominator on the left is really big. And the reason for that is because when you have two totally separate samples, you've got to take care of the variability in the first sample and the variability in the second sample. It's all got to factor into the standard error. So yeah, you get a big standard error. And so then when you're computing the test statistic, it means you're going to get a bigger denominator. So your test statistic ought to be a value closer to 0, right? I mean, like, I guess that's the part that's the algebra part. But then when you have paired data, there's a lot less variability because then it's half as many individuals and it's just a single group, and right? So what you end up with is a much smaller denominator, so the value of the test statistic gets a lot farther from 0. So here, those two test statistics are pretty distinct, right? Like one is a whole lot bigger than the other. And that means the p-values are a lot different too, right? And it's even the same degrees of freedom, right? At least if you do the independent degrees of freedom by hand. It's the same degrees of freedom, and you don't use the Satterthwaite thing. But look at the p-values. Like one of those, you're obviously not going to reject the null. The one on the left, because that p-value is absolutely enormous, right? It's way bigger than 0.05. But then the one on the right, you're clearly going to reject the null because that's tiny, right? It's 0.000151, right? It's written in scientific notation, that little itty-bitty number. So that's what can happen, and this is kind of an extreme example where I kind of manipulated the numbers to make it this crazy. But it's possible, right? It's possible where if you accidentally classified paired data as independent data, you're going to end up with the wrong conclusion, and vice versa, right? So there is a consequence to classifying the data the wrong way. So that's why I put this whole page in here. It's just like a follow-up to being able to tell paired and independent data apart. But then the last thing, and there's actually a bunch of this in the homework, where you have to import the data. And I know there's just like a button you click in the homework and it pastes directly into StatCrunch. But we'll do it from a CSV, because if you can do it from a CSV, then you can definitely do it from StatCrunch. All right, so what we've got is that a company institutes an exercise break for its workers to see if this will improve job satisfaction. So we have 10 workers where we have the job satisfaction score before they had the exercise break, and then after they started getting the exercise break. So we want to see, did they like their job more, right? We're looking for evidence of an increase in average job satisfaction. And let's say, hypothetically, what if I just set this one up the other way? So let's say if I said, what if, oh, forgot to change color. if I said, what if the difference, if I just read it left to right, and I said I want it to be before minus after this time. Which might be easier because this is the way it's arranged in the CSV file too. So when you pick your two columns in StatCrunch, you just go first one, second one. So in that sense, maybe it's slightly easier. But then you got to be careful with the alternative hypothesis. I will say that. So the null is just going to be that mu sub d is 0. There's no change. The alternative, an increase would be if the after average score was bigger. So if we're doing the differences before minus after, you would actually need it to be negative, not positive. So an increase when you're using that order of subtraction would be a negative number. And this is why usually you don't pick before minus after, but I figured it would be good to do it just to get that variation in here. Next thing, I guess, would be going to StatCrunch. So let's go ahead and do that. And we'll get our p-value and everything. We'll get a whole bunch of other stuff too. But let's see. So I need my data, which is in here. So here's my CSV file. I'm just going to copy this. So Control C, and we're going to paste it in here. So go up in the heading, Control V. There's our data. And then if we go stat, tstats, and then we want to go paired. So where there's that third option that just says paired, go to that one. And then sample 1 was before, sample 2 is after. Oh, and by the way, whatever you pick as sample 1 and sample 2, StatCrunch is programmed to do the difference as sample 1 minus sample 2. Then we needed a less than here, right? And then there we go. All right, so what those are, like the mean, that's d bar. So that's the sample mean difference. The standard error, that's, let's see, that's going to be our S sub d. And then, well, I guess it's our S sub d over the square root of n. And then we've got our other stuff in there too. Right, our degrees of freedom, which I guess we didn't really need that StatCrunch to compute it for us. Right, it's 10 minus 1. And then we got our test statistic, we got our p-value. So I guess maybe just these for now. Those would be nice to have, maybe, our test statistic, and we definitely need the p-value. So going back here, let's see. All right, so our test statistic ended up being negative 3.597, and then our p-value is going to be 0.0029. All right. So then, let's see. I guess the other thing is, and I should put this in here too, since I didn't state it up above, but you would have to do it just like with that other example. Here we'd have to assume that the population is normally distributed. Since n sub d, which here is 10, is too small to apply the central limit theorem. Right, we would have to do that here. And actually, there's one other thing I wanted to show in StatCrunch. So let's see. All right, now, oh yeah, options, edit. And if you actually want the individual differences, you can check this box right here. Then if I go to compute, then they show up in their own column. Not that you really need StatCrunch to figure the differences out, right? I mean, you can just subtract across and you can get them if you really want them that bad, I suppose. But you can make StatCrunch do it if you want. I guess that would be useful if you were looking for values that were really weird, or like something really extreme. And so then you'd look for where like you're getting these huge differences. I guess huge in terms of absolute value, right? Numbers that are really far away from zero. So it would be useful for that. Like if you were going to do like a subsequent step, which for what we're doing right now, we're just kind of worried about the hypothesis test. But that would be the next logical thing, right? Like, is there anything in this data set that looks really weird, right? And I guess if you had the differences, you could figure that out. But let's see, going back here, let's see, we just had to do the decision and the conclusion, I think. So for the decision, 0.0029 is less than 0.05. So the p-value is less than alpha, right? And when the p-value is less than alpha, that's when we reject the null. So the null should be rejected. And then for the conclusion, we can say that there is sufficient evidence, or enough evidence, if you want to say it that way, to conclude that there has been an increase in mean job satisfaction or in average job satisfaction. I'm going to say average since it says average up above in the original problem. Ah, I missed a letter. No wonder it looks weird. Missed the S. There we are. Oh, let me draw. Satisfaction. There. Okay. Writing too fast. But this problem, like on this page, this is usually what you have to do on the homework for this section. There are several where you have to import the data, but when it's already there within the MyLab system, it's easier because then it's just to use that window-looking thing that you can click on in the upper right, and then you just select paste into StatCrunch, and then it's just there, right? So that's actually easier than pulling it out of a CSV file. But there are several problems where you do have to do it.